think the following lemmas that I'll need today are things that were already proven. One of them was that, again, so this R is a ring, and I'm going to be looking at R modules, or mod R. Most statements are going to be the same, and P is projective if and only if X N R P M is 0 for every M module. I guess let's stick to right modules, and then everything is the same for left modules. And n bigger or equal than 1. But the lemma was that this was if and only if x1 R PM is 0 for every n. I think this I proved last time. The same thing for injectives. I is injective if and only if xn mi is equal to 0 for every m and n bigger or equal than 1. But then this is if and only if x1 mi is 0 for every m. And of course, this implies this, but then the comeback is something we proved last time. What else did I need? So I needed this statement that this took us some time to prove, that f is flat and finitely presented. Then it was projective. In particular, if f is flat and the ring and finitely generated and the ring is Noetherian, then f is projective. And projectives are flat, so that's clear too, without any finite generation. So this we needed too. What else did I need? I think I also needed this lemma that we proved last time, that if we have a resolution of this form, I think it was Pn minus 1, then some module m, 0, Pn is 0 into our module n, 0, where the pi's are projective. Then x n plus 1 and anything n m k was the same thing. I'm using x on top and on the bottom. I guess I'm using upper indices and lower indices. I think through all my lectures I always used lower, and I didn't use the and I never used the range, so just keep them as lower indices. Then this is the same as x 1 m k, and this is for any k. Hopefully it was like that and not an n here. We'll get to fix it if it's wrong. But that's something, and the same doubt appeared when we proved this statement. All right, so what else? I think that's everything I need for today. So I left when I gave a definition. So let's repeat those definitions. Definition. If M is a right arm module, then the projective dimension of M is the minimum n such that, if it exists, such an n, such that there exists a resolution Pn0 maps to Pn minus 1, P0, M0 by projectives. So if you have a resolution with finitely many projectives and of length n, and this is the minimum such n, then we'll say this is the projective dimension of M. It might be that M does not admit a finite resolution like this, and then in that case we'll say that the dimension is infinite. The injective resolution, injective dimension of M is the same for injectives. So you take I0 into I1 into ID, well, I guess it's N0, where the I's are injectives. And again, this is the minimum such n, and the flat dimension the same with flat. The flat dimension of M is the same with flats, with flat resolution. Now, of course, since every projective module P is also flat, then since projectives implies flat, then the flat dimension of M is less or equal than the projective dimension of M, because any projective resolution already counts. So in particular, if the projective dimension of a module M is finite, then the flat dimension is finite. And then the actual definition is this definition. The projective dimension, and here it does depend whether or not we're taking left or right arm modules. So this is the right projective dimension because we're looking at right arm modules of the ring R is equal to the supremum of all the projective dimensions of the modules on M, where M is a right arm module. And of course, you can look at the left projective dimension of the ring R being the supremum over all the projective dimensions of left arm modules. So this projective dimension of the ring is also called the global dimension. So this is also called the right or left, depending if you look at left or right D modules, or left or right R modules. But this is the global dimension of R. And the third dimension of R is the same, but with the flat dimensions of modules. The supremum of the flat dimension of M, where M is a right arm module. And today I want to prove the following theorems. Now again, clearly the third dimension is less the third dimension of the ring is less or equal than the global dimension of the ring, just because each flat dimension is less or equal than the projective dimension. So the supremum over a set which is each element is less or equal than the sets in the set there, then it has to be smaller or equal. In particular, if the global dimension of a ring is finite, then the third dimension of the ring is finite. Notice that if you have one module that does not admit a finite projective resolution, or if you have one module that does not admit a finite flat resolution, then both dimensions are infinite. So some examples is, just give two. So if the ring R is a field, then the global dimension, it doesn't matter if it's left or right, essentially. For any commutative ring, global left or right dimensions are the same, but the global dimension of R is the same as the third dimension of R, and it's equal to 0. Because any module is projective in that case. So any module already is itself a resolution. You can take P0 to be the module itself and just take an isomorphism. And therefore any module is flat. So all modules admit at length 0 resolution. But now if the ring is Z, then the situation becomes interesting because, well, at least it's non-zero. We know that we have resolutions of length 1. So I've proven that any abelian group has an injective resolution of length 1 and it has a projective resolution of length 1. So another example perhaps is, again, with the ring R being Z, but let's look at Q as an R module. So it's an abelian group. Q is not projective. It's not projective. But the projective dimension of Q is 1. Well, it's not projective, so the projective dimension cannot be 0. If it was if the projective dimension is 0, then it has a resolution of length 0, and it is isomorphic to P0, and therefore the guy is projective. But it's not projective, so the projective dimension of this guy has to be bigger or equal than 1, and it is actually 1. So the question is why? What is this resolution of Q as abelian groups that are projected? And this we've already done as well. So I'll leave you as an exercise. What is that resolution of Q? That gives the example that the global dimension of this guy ought to be at least 1. Okay. So what's the theorem that I want to prove? Theorem. The global dimension of R is equal to either the supremum of the injective dimension of right modules M or 2, the supremum So it doesn't matter if you take projective or injective resolutions. The supremum of the projective dimensions of ideals, so quotients by ideals, a right ideal, B3. Same thing with injective dimensions. Four. I might have gotten this wrong. So the let me stop right here. Let's prove that, and then I'll give you another description of that. But this is saying that it's the same to compute the global dimension of a ring using projective resolutions or injective resolutions. And it's enough to do it for ideals. So it's enough to do it for modules that are of the form R mod an ideal. Okay, so we want to prove this. And the lemma we want to prove, which is what we are going to use. And before doing that, let me just state that same theorem for the Tor dimension. So theorem, the Tor dimension of a ring. Tor dimension of a ring R is also equal to the supremum. It doesn't matter if we take left or right modules, that's why I didn't write it there, but let's do that. So this, I've defined it to be the supremum of the Tor dimension, I think of the flat dimension of M, where M is a right R module. So that was the definition, and then it's the same thing as the supremum of the flat dimension of M, where M is a left R module. And then it's also the supremum of the flat dimension of R mod I, where I is a left ideal. And it's the same thing if you do this for right ideals. And let's write this in a different way. So this is the minimum n such that every Tor n I think I might get this by 1. So this is going to be the minimum n such that Tor n, mn, is equal to 0 for every m and n. So now m is a left R module and n is a right R module. No, the other way around. M is a right R module and n is a left R module, so that I can actually take this Tor. And let's fix this. So this is such that this happens. And I think I could do the same thing here. So this is again the minimum n such that x n plus 1 mn is 0, and here for every m and n. These are all R modules. So this is the right global dimension. So this is X on right R modules. Okay, so I have three notions. I have the notion of a right global dimension, left global dimension, and just one notion of third dimension of a ring. So for the third dimension, it doesn't matter if I look at left or right or right R modules. I'm going to just take, it doesn't matter, the flat resolutions work the same for left or right. And this has to do with the fact that Tor was balanced, and I could compute this Tor by taking either projective resolutions of m or projective resolutions of n. And it didn't matter whether for x here, I need to take either a projective resolution of m or an injective resolution of n. So this is really not symmetric in left and right R modules. And that's why this, well, the two global dimensions might be different. Left and right global dimensions of a ring might be different. So that's a warning. The left global dimension of a ring R may be different. And it's sadly so than the right global dimension of a ring. Let's check that at least the ring needs to be infinitely generated for that to happen. So I claim that if the ring is right Noetherian, so if R is right Noetherian, namely that satisfies the descending chain condition for ideals which are right ideals. Then the third dimension of R is equal to the right projective dimension of R. So the same proof is going to tell you that if R is left Noetherian, then the third dimension of R is the same as the left projective dimension of R. So if the ring is left and right Noetherian, then the third dimension is the same. Both projective dimensions, therefore, they are equal, and that follows from the fact that the third from this theorem that the third dimension can be computed either by looking at left or right modules, by supremums of left or right modules. Okay. So let's prove this statement first. Let's assume that the both theorems, that theorem 1 and this theorem 2, let's put names to this. This is 2 and this is 1. And let's prove that theorem. Okay. So how am I going to prove this? All right. So this dimension is always less or equal than that dimension. Okay? So in particular, if this dimension is infinite, this guy is going to be infinite and they're going to be equal. So let's assume that this dimension is finite. So let's assume that the third dimension is equal to n and is finite. So I need to prove that the projective dimension is finite and is equal to n. Okay? And this projective dimension is always bigger or equal than this guy. So I need to prove that the projective dimension is less or equal than n. I need to use the fact that this thing is Noetherian, of course. So how am I going to do this? guess I want to prove the following statements. Yeah, so let's prove the following lemma. Let's prove the following lemma. Let's suppose that the projective dimension of a module M is less or equal than N. And let's take any resolution of M of length N but such that each one of these guys is projective. Then I claim that N is also projective. Now, of course, the converse would also be obvious, right? If N is projective, then the projective dimension of M would be less or equal than N, because I would be giving you a resolution of length N. Okay, so how do I prove that this N here is projective? Well, then we look at X. This is the lemma which is proved before. That X N, I guess it's Xn here, Xn plus 1 of M anything, okay, is equal to X1 N anything. And now it follows from this lemma, since the projective dimension is N, that this guy is equal to 0. So this is equal to 0 for every k, and this implies that N is projective. And notice that the same thing holds immediately with the same argument. You get that if you have a resolution, let's say that the injective dimension of M is less or equal than N, and you have a resolution by injectives, I0, I1, up to In minus 1, up to some modulo N, then N is injective. Same argument, and this is an if and only if. If N is injective, then clearly this tells you that the injective dimension of N is less or equal than M, of M is less or equal than N, but also by taking X into M, so X N plus 1 of K into M, for any K, is the same thing as X1 Ki, and this is 0 for every K. And again, it's 0 because of that lemma there, that if the projective dimension is N, then these X are all zeros. Well, actually, yeah, no one is stopping me. I am using something much stronger, because this N might be bigger than the n there. This n was the supremum for the ring. So let's prove this. So I'm making an affirmation there that I actually haven't proven. I'm making the affirmation that xn plus 1 of mk is 0. So this we proved already, the equality of these two. But I haven't proven to you actually that this is 0 or that this is 0. So let's prove that because it's trivial. If the projective dimension of M is equal to n, it means it's less or equal than n. It means that M does have a projective resolution. It might not be this one. It's some projective resolution. So let me call it P bar 0 up to P bar n and then 0, where all of these guys are projected. And this X group that I needed there, X K M into any module is given as the homology of the complex which is home from P into K. And now this complex here will not have homology in degree n plus 1 because simply this complex does not have n plus 1 elements. So the homology in degree n plus 1 is 0. Because home itself is 0 at that degree. This complex has n elements. It does not have anything in degree n plus 1. So that's the proof that this guy is 0 for that m, and therefore x1 is 0 for any k, and therefore n is projective. And the same thing happens for injectors. But I haven't done the same thing for Tor, so let's prove that statement, which is also true. If the flat dimension of m is less or equal than n, then the same thing happens if you have a resolution now by flats fn minus 1, fn minus 2, f0 m, then n is flat. I would want to say that I'm going to take this resolution by flats and compute Tor now. I know I can compute Tor by resolutions by flats. So what I know is that Tor n plus 1, n anything, the same argument is going to prove that this is the same thing as Tor 1, n anything. And this is 0. This is 0 by the same argument because I can compute this Tor by taking flat resolutions now of m. And I'm telling you that there's a resolution by flats that has n elements. Therefore, the Tor n plus 1 is 0. But I haven't proven that this is equivalent to n being flat. So the fact that this is equal to 0 for any k implies that n is flat. I think I haven't proven that, so let's prove that. So I need to prove that what I know is that n is flat if and only if Tor. So what I've proven, what the definition is that n is flat if and only if Tor n and k is equal to 0 for every k and every n bigger or equal than 1. So that was the definition of being flat, that it was a cyclic for Tor. But I would want to prove that this is if and only if Tor 1 and k is equal to 0 for every k. Okay. Yeah, so the proof of this statement is exactly the same thing as before. You just do dimension shifting. So sketch of the proof. resolve K. Okay, and use dimension shifting. And do by induction. So if you know that tor 1 is 0, you're going to end up proving that tor n is 0 for every k. Okay, so, all right, so if I have a resolution of something that has dimension less, homological dimension less or equal than n, and I have a resolution where every element is projective except the last one, then the last one is projective. Or if every element is flat except the last one, then the last one is flat, and so forth. Okay, so there's one extra trick. There's something different that happens when I need to check for injectivity, and the same thing happens for flatness. So, and I think both of them I did prove. So I said I is injective if and only if x mi is 0 for every m and every n bigger or equal than 1. And this is if and only if x1 mi is 0 for every m. But also, this is if and only if x1, you not only need to check this for elements of this form, for an arbitrary module, but actually for quotients by ideals. I mean, and of course, the arrows in this direction are trivial. So if I is injective, this is the definition, xn vanishes. And if xn vanishes, then x1 vanishes. And if it vanishes for an arbitrary module m, then it's going to vanish for this module. So I just need to prove this equivalence the other way around. But again, so how did we prove that x1 implied that xn vanished? This was, again, looking at, well, I'll be looking at this. I'll just take an ideal J. I'm not sure if I'm going to remember how did we do this? We looked at I. We had a map, let's say A, an injection of A into B. This was my injection. And then I looked at the co-kernel. I completed this into a co-kernel like this. And I is injective meant that hom bi maps into hom ai by just composition with this was surjective. But then the co-kernel of this map is x1 ci. And then I is injective if and only if this map here is surjective, but this sequence is exact, and this is surjective if and only if this guy here is 0. So, okay. On the other hand, I've given you Bayer's criterion, and I said, actually, it's enough to check that this guy is injective when I take A to be an ideal, and it's inside of the ring itself. So that was Bayer's criterion, that I only need to check this existence of this map, of this lifting, when I take an ideal inside of the ring. But then in that case, I'm going to have that this C here is going to become the ring modulo the ID. And that's this statement, that x1 here is 0. So I need to check x1 being 0 only for quotients by ideals, and the same thing happens for tor. So that's not, I think I've given this lemma, but just in case, let's prove it again. Suppose that you have that situation where you have an ideal inside of a ring, And then you just perform the quotient. And now just tensor that sequence with your module M. I think I'm taking my guys to be write our modules. So I'm going to tensor this sequence by M. Okay. So I have, this is all over R. So here I'm going to get M again. Here I'm going to get M tensor over R with the ideal. And here I'm going to get Tor1 and Rj. That sequence is exact. The next guy is going to be Tor1 of MR. But now I know that I balanced Tor, and I can just take either resolution. And this guy is projected. So it doesn't matter what's the status of M, but this Tor is going to be 0, because R is projected. So this sequence is exact when I put a 0 here. This holds for any ideal J. Okay. On the other hand, well, if M is flat, then clearly this guy is 0. But also, if this guy is 0, then this sequence is exact. Then this sequence is exact. I put this to be 0. This sequence is exact. And remember that this is, this quotient here is the same thing as M divided by Jm. And the fact that this was exact was equivalent to M being flat. That was one of the equivalents of M being a flat module. So what you see is that if M is flat, can be checked by only looking at Tor, not with an arbitrary module, but just with modules that are of this form. The ring module of an idea. Okay, so that was this statement. Here. So this finishes the proof that if you have a resolution of something of flat dimension less or equal than n by n elements, the n minus 1, the first guys are of length n, where the first n guys are flat, and then the last one is also flat. Okay? It's taking longer than I wanted. Okay, so now, if, let's say now that the flat dimension of the ring R is equal to n, I'm sorry, the Tor dimension. The Tor dimension of the ring R. Well, let's write this completely. So let's suppose that the Tor dimension So the following are equivalent. For every one. For every, so here we fix a module M is fixed and it's a right arm module. Now for every resolution of this form, where the PIs are projective, then n is projective. Two, the projective dimension of m is less or equal than n. Then 3, x n plus 1 m anything is equal to 0. Actually, let's say x n anything is equal to 0 for every k and every n bigger or equal than n. I'm sorry, n bigger than n. And 4 x n plus 1 mk is equal to 0 for every k. Now, this implies this is clear because if n is projective, I gave you a resolution of the right length. If the projected dimension of m is less or equal than n, then you have a projected resolution of length less or equal than n. Therefore, all higher x groups are 0. Same thing. You use that resolution for n. And this obviously implies this. So the only thing to prove is that this implies this. And that's what we've proven already. Because if you take any resolution of this form, then x, well, this is a statement that I think I've proven here. If I have a resolution of that form, then x, since all of the p's are projective, xn plus 1 of mk is the same thing as x1 nk. And if this guy is 0 for every k, then this guy is 0 for every k, and then therefore n is projective, which is what we want. So all of these guys are equivalent. And the same thing happens therefore for injectives. So perhaps I'm not going to state even the case for injectives, but let's just write it here. For every resolution, arrows in this direction, and now this is I0 up to in minus 1 up to n 0, where the i's are injectives, then implies that n is injective. The injective dimension of m is less or equal than n. It's the same thing as x into m from k equal to 0, and this is the same thing as xn plus 1 from k into m is equal to 0. So these two lemmas are exactly the same. But there's one extra for this guy here. Actually, in the injective case, we can add one extra case here, and is that x n plus 1, that I can either test this or this when the case k is just r mod an idea. I can do this for ideals of this form because I have this condition that if x1 is equal to 0 for these guys, well, this boundary extension, that if I check something for injections of an ideal into the ring, then I can check for injectivity using those modules. So this lemma for injectives works with this extra condition as well. So these are also is equivalent. So for Tor, we have the same condition, the same thing. The following are equivalent. Same thing for flat resolution. So one for every flat resolution. For every resolution by flats. It's not a flat resolution. For every resolution of the form 0 into n, fn minus 1, f0, m0, then n is flat. 2, the flat dimension of m is less or equal than n, and the proof is the same. 3, Tor n m k is equal to 0 for every k and every n bigger than n. And 4, Tor 1 m k is equal to 0, oops, tor n plus 1. mk is equal to 0 for every k, and 5 tor n plus 1 m r mod j is equal to 0 for every id. And the proof is exactly the same using this extra condition. So this implies this, implies this, implies this, implies this. It's obvious. I only need to check that this, which is equivalent to this, which I've already checked, imply this guy. And now this implies this guy. Same condition is that tor n plus 1 of mk is the same thing as tor 1 nk. And if this is 0 for everyone, then tor 1 nk is 0 for every n, and therefore n is flat. Okay. So we have this equivalence of all these things, and I can check, therefore, for, well, I can check flatness in this way. All right, so now let's suppose that the ring is Noetherian, and that the flat dimension, the tor dimension of the ring, let's grab a module M that has flat dimension n, less or equal than n. No, n, just so let's suppose that R is Noetherian, right Noetherian, and that the flat dimension of a module M is equal to n, which is finite. In particular, it's less or equal than n, and I can use this lemma. For every resolution by flats this way, then this last one is flat. Okay. So let's grab a projective. Let's suppose that the projective dimension of M, this guy is always bigger or equal than that guy. So let's suppose that it's actually bigger. But then, and let's suppose that M is finitely generated. Suppose that M is finitely generated. So that's an extra condition on the module M. Okay, so in this situation, what I can do is I can construct a resolution of M by free modules. By finitely generated free modules. Well, the fact that M is finitely generated and that R is Noetherian, it means that M is finitely presented. So it means that I have something like this, which is exact here. So that's M being finitely generated means that here I have a surjection. Take the kernel of that, and I claim that that thing is finitely generated because, well, the ring R is Noetherian, and this is a finitely generated module. The kernel of this map is going to be a finitely generated submodule of this guy. Because, well, it is a submodule, and therefore it's finitely generated because the ring is Noetherian. So with this argument, you can just proceed by induction by just taking each kernel, and then you're going to get a resolution of this M by finitely generated R modules. In particular, they're all projective, and therefore they're all flat. But you can stop at n minus 1. Just take the kernel of the last one. Call it n. And now you have all these free modules that are also flat. They're all of this one. And the lemma says that this n here is flat. But it's finally generated. And therefore, this implies that n is projective. From the lemma of the last lecture. Okay, so n does have a projective resolution of length n. So what we're proving is that for any finitely generated R module, the flat dimension of M is equal to the projective dimension of M. Finitely generated R module, the flat dimension of M has to be equal to the projective dimension of M. Okay, so now the global dimension, the right global dimension of the ring was the supremum of these guys over all modules, not finitely generated ones. But on the other hand, by the lemma before, well, if we take the proof of the theorem, what we needed is to check this for M of the form R mod J for J an ideal. Okay? And those are finitely generated. So it's enough to check for finitely generated that the global dimension, what the global dimension is. And for flat dimension, it doesn't matter because this one is always less or equal than that. So this proves the statement that for Noetherian modules, the flat dimension is the same. For Noetherian rings, flat dimensions and global dimensions are the same things. Okay, so that's it. So the proof of the theorem is exactly the same thing as I've been saying of this dimension shifting. The proof of the theorem is that, let's check that it doesn't matter if I take injective resolutions or projective resolutions, and I can check for ideals, for quotients of ideals instead of quotients by ideal instead of just arbitrary modules. Okay, so what I wanted to prove was this theorem that the supremum of all of the following are the same. Supremum of the following are the same. Projective dimension of a right module M. Injective dimension of a right module M. Projective dimension of R modulo an ideal, and the same thing for injective dimensions of R modulo an ideal, and for I claim that either of this guy is, well, for x. If any of these guys is less or equal than n, then xn plus 1 of m. N is equal to 0 for every m. Okay, so that's what we wanted to prove. Well, what didn't I prove already? Let's see. It looks to me like we've already proven everything here. Let's see. So the fact that, let's say that the projective dimension of this guy is less or equal than n, then it implies this. For any, so for if you have a module that has the projective dimension less or equal than n, then this would be true for every guy, for every n. But now you can play the game that if you know this, and this holds for every m and n, now you can compute this by using injective resolutions of n. And then you're going to get that this guy has to be less or equal than n. And there you get the equivalence between these two. And we've already proven the equivalence between these guys. So therefore you get the equivalence between these two. And the same thing here. So the fact that this, that this is equivalent to this is the fact that you can check injectivity by the Bayer's construction, by the Bayer's criterion. And that gives you the equivalence between these two. And that's it. Okay, so those are the statements for dimension, and we want now to study what are rings of small dimensions. And then I'll just stop right there. So I've given you one example, which is Z being dimension 1. So the global dimension of Z. And this is Noetherian. This is the third dimension of Z is equal to 1. And left and right, it doesn't matter, it's commutative. But, okay, so let me give you, and I've told you that for a field, this was 0. The global dimension of a field is 0. So definition. A ring R is semi-simple if every ideal is a direct summand. Of R. So semi-simple rings are classified. Some semi-simple rings that are finitely generated over a field, for example, are just matrices, or direct sum of matrix algebras. And they have a very simple representation theory. So this is the very first kind of example that gives us a classification, that gives us this classification by dimensions. So let's try to understand what this guy is. So if you have a semi-simple ring, and you pick any ideal, this sequence is split. Because since I is a direct summand of R, then you can split this guy here. So R, I plus something is isomorphic to R. You can find a complementary subspace to I. And then that something needs to be isomorphic to R mod I. This in particular says that I is projective. Because, it is a direct summand of a free module. But also tells you that this guy is split. And if this guy is split, this guy is also projective. So if your ring is semi-simple, then every ideal is a projective R module. And every, quotient by an ideal is a projective R module. But if R mod I is projective for any ideal, this implies that x1 R mod I k is 0 for every k and every ideal. But this means, therefore, that every k is injective. By Bayes' criterion, we checked an x1 for every ideal. Once I fix k, this tells me that this guy is injective. And now the same thing, I can just check for Tor. So checking with Tor, or just doing x1 into r mod k, into r mod I, or x1k r mod I, you get that every k is projective. Or put it in a different way, since every module k is injective, then every module has an injective dimension 0. This implies that the global dimension of the ring is 0, because I can compute this as a supremum of all the injective dimensions. But the global dimension of the ring is 0 means that the projective dimension of every k is 0. And this implies that every k is projective. So semi-simple rings satisfy the property that every ideal is a direct summand. Every ideal is projective and injective. Every quotient by an ideal is injective and projective. Every module is injective and projective. And those are rings of these. So semi-simple rings are rings of global dimension 0. Now these guys have been classified. I told you for algebras. I'm not going to tell you what the Weatherman theorem is. I think we proved that in algebra 1 or in algebra 2. I'm not really sure. But one of these master classes we proved that then. But the Weatherman theorem says that if R is semi-simple, then it is direct sum. Direct sum of matrices of n by n with coefficient subdivision algebra. Subdivision. So in particular, if R is semi-simple over a field, is an algebra over a field, which is semi-simple, then it's going to be the direct sum of matrix algebras. So that's a particular example. If R is an K algebra, semi-simple, then it is a direct sum of matrix algebras. So it means that there exists V1 up to Vn vector spaces, finite dimensional vector spaces. So let's put here a finite, such that R is just simply the direct sum of the endomorphism algebras of those VIs. Now, in general, so if you have that R is semi-simple, and every ideal is a direct summand of R. So for every ideal, so this R therefore decomposes as the direct sum of all of ideals. Right? For every ideal then R that you have, you write R as the sum of I plus something else, and now just decompose each one of these two guys. Right? So you can check quickly that I is also semi-simple and R mod I is also semi-simple. So every semi-simple ring is a direct sum of the minimal ideals. R semi-simple implies that R is direct sum of minimal ideals. And in the case where R is an algebra over K that is of this form, these are the minimal ideals. So this ring is just a direct sum of matrix algebras, and the multiplication of one endomorphism in one guy with an endomorphism of another Vn is 0. So these are the minimal ideals. And these are simple. So these are minimal ideals in the sense that they are not contained anywhere else. And that means that these guys do not have an ideal inside of them. And yes, you can check that matrix algebras do not have ideals. So they are simple. How do you check that? So exercise. Matrix algebras, n by n matrix algebra with coefficients in a field does not have non-trivial ideals. More generally, you can check that if you have a subalgebra of endomorphisms of a vector space that does not leave any subspace invariant, it does not have ideals. So that's a very simple exercise. If you had an ideal, then you can just check that you can construct an invariant subspace, which matrices doesn't have. Okay, so that's an example of rings of global dimension 0. I think it's probably a good spot to stop. So next time I'll just talk about hereditary rings, and these are going to be rings of global dimension less or equal than 1. The representation theory is slightly more complicated than this, but a consequence of having global dimension of being semi-simple. So we've checked this, that R is semi-simple. Therefore, the global dimension of R is 0. And therefore, a trivial consequence of this is that every module is injective and projective, is that there are no extensions. Because x1 mn is 0 for every m and n. And we've checked that this being 0 meant that there were no non-trivial extensions like this, like this, in the category of our modules. Every time that you had an extension like this, then it had to be n plus m. So the algebra of polynomials in one variable certainly cannot be semi-simple, because we do have obvious extensions. Kx multiplication by x. And this guy is non-trivial in the category of kx modules. So this we know it's not a semi-simple ring. But then from semi-simple rings we have no non-trivial extensions of representations. So examples of semi-simple rings that are non-trivial examples of semi-simple rings, well, depends on what you call non-trivial, is G a finite group? So if G is a finite group, then and K is any field, this is a semi-simple ring. Semi-simple, well, that's actually false. Semi-simple ring. If the characteristic of a field does not divide the order of the group. If you've done finite group theory, this guy is a G representation, is a direct sum of all the irreducible representations of G with some multiplicities. And any representation of G is unitary in the sense that it always admits an inner product that is invariant by the group G. So if you have any submodule, then the complement is also a submodule. Therefore, any module is a direct sum of the irreducible pieces. And you have no non-trivial extensions of representations of a finite group. The same statement happens when G is a simple Lie algebra. If G is a simple Lie algebra over a field K, then, well, this guy is not a ring, but the universal enveloping algebra of G is a ring, it's a K algebra. And there are no non-trivial extensions of, well, let's say that this is over an algebraically closed field of characteristic 0. Then again, there are no non-trivial extensions. No non-trivial extensions. But here, there's a problem. There are no non-trivial extensions, finite dimensional. So there are non-trivial extensions of non-split extensions of modules for this ring that are infinite dimensional. So the typical example is the Verma modules. So this guy cannot be of global dimension 0 by what I said. This cannot be semi-simple because I do have non-trivial extensions. So that's a nice example where you have an algebra that the category of representations of this algebra does have non-trivial extensions, but if you look at the subcategory of finite dimensional representations, there are no non-trivial extensions. Okay, good. So this is sort of like the analog of this, what happened here, and the same thing for G, a compact, instead of a finite group, if G is a compact Lie group, a compact group, same thing happens. It's just that this guy here, the ring of functions on G, L1 integrable functions on G, has, with a convolution, has an associative algebra structure. That's the analog of this. Now, the same thing happens. This guy does have non-trivial extensions, just as this, but it doesn't have infinite dimensional. It doesn't have finite dimensional non-trivial extensions. Yeah, so I guess I'll talk a little bit about this eventually. Okay.